Hey everybody, welcome to our lesson video for 9.3. Today we're going to move from simple rational functions to general rational functions. So we're adding a little bit more complexity to the right types of rational functions that we're going to learn how to graph today. So to graph rational functions, we've got our 9 steps. And you can see here that we've already covered all the ones in blue. Today we're going to add in step 2 and step 7. We're going to talk about holes, and we're going to talk about creating an interval table. So then the only step left will be step 6 for even slightly more complex rational functions. So as we're going through this, it would really help if you had your 9 steps to graphing rational functions handout next to you so that you can be looking at that as we're working through the examples. And you'll want to use graph paper for your notes, obviously, because we'll be graphing. So the first example here is s of x equals 3x plus 12 divided by x squared plus 5x. So we're going to go through each step. So step 1 says, factor if necessary, determine the domain. In this case, this can factor, at least to some extent. We can factor this into 3 multiplied by x plus 4 divided by x times x plus 5. And the reason that we want to factor these is to check in case anything cancels out to simplify our rational function. Now in this case it doesn't, but in some cases it will. The other reason to factor is it can sometimes help you to see the domain a little bit more clearly. In this case, our domain is that x cannot equal 0 and x cannot equal -5, because those are the two values that would create the denominator to be equal to 0. So after the domain, step 2 says find holes and plot them. Now in this case, the only time holes occur is when pieces cancel out after you factor. Nothing canceled out in this case, so there are no holes. So then step 3 says, all right, find the vertical asymptotes and draw them. The vertical asymptotes occur at the locations where the domain does not exist unless there's a hole at that location. So in this case, we have 2 vertical asymptotes. We have a vertical asymptote at x equals 0. We also have a vertical asymptote at x equals -5. So I'm going to draw those in first. 1, 2, 3, 4, 5. Okay. So then step 4 says find the y-intercept, x-intercepts, there might be several, and plot both. So in this case, our x-intercept is the place or places where the numerator equals 0. So in other words, we're looking at the location where 0 equals 3x plus 12, which when you subtract 12 and then divide by 3, you end up with an x-intercept of -4, 0. So I'll plot that on here as well. So we have an x-intercept at -4, 0. And then for our y-intercepts, that's where the when x equals 0. So in this case, when we think about plugging in 0 for x, we would have 3 times 0 plus 12 divided by 0 squared plus 5 times 0, which essentially equal, or I apologize, let me rewrite the numerator here. 3 times 0 plus 12. So essentially here we would end up with 12 over 0, which is undefined. So in other words, we have no y-intercept. And that makes sense because if you look at our graph, we have a vertical asymptote at y equals 0, or at x equals 0, so it's pretty clear that we couldn't possibly have a y-intercept in this situation. So then the next thing here is the horizontal asymptote. And the horizontal asymptote, if we look at this, we're in the situation where the degree of the numerator is less than the degree of the denominator. And we learned last lesson in 9.2 that that tells us that our horizontal asymptote has to be y equals 0. So I'm going to sketch in our horizontal asymptote as well. And you'll notice that we have a point on our horizontal asymptote, which might seem weird, but we talked in 9.2 about the fact that the horizontal asymptote really only applies at the end behavior, when x is infinity or negative infinity. So it's actually okay that our function might cross the horizontal asymptote in the middle. Now, the last step here is we need to add in our interval table because we need to think about, we don't actually know at this point, when we look at the graph, we have no idea where the curves are going to go for each section. They might go above the horizontal asymptote, they might go below the horizontal asymptote, they might cross it. We need to essentially test points to figure that out. And specifically, we're going to create what's called test intervals. So I'm going to create a three-part table here where we've got, so let's see here, I'll draw in. So we're going to have a test interval. We're going to have a test value within that interval. And then we're also going to find the y value, f of x, for each test value. And this is what's called an interval table, and we're doing this so we can figure out where the curves go. Now, the test intervals are between every vertical asymptote as well as any x-intercepts. So in this case, our first interval would be from negative infinity to negative 5. Our second interval would be from negative 5 to negative 4. Our third interval would be from negative 4 to 0, because we're going from the x-intercept to the next vertical asymptote. And then our last interval would be from 0 to infinity. So within each test interval, we're going to test a value. So I usually just try to pick as simple ones as possible. So like from negative infinity to negative 5, I might just test negative 6. From negative 5 to negative 4, I might test negative 4.5, or in other words, negative 9 halves. From negative 4 to 0, I'll probably just test negative 1. And from 0 to infinity, I'd probably just test positive 1. So we're placing these test values into the original function for x, and you can place them into the original function or the factored version. It's totally up to you. And you can, if you want to, you can use your calculator to help you figure these out quickly, or you can do them by hand. It's kind of up to you. So for example, if I put in negative 6, I would probably put it into the factored version. So I would have 3 times negative 2, which is negative 6, divided by negative 6 times negative 6 plus 5, which is negative 1. Negative 6 times negative 1 is just 6. So I would have negative 6 over 6. In other words, I would have negative 1. And you can plug this in for each one of these. So next I would plug in negative 9 halves for x. And rather than waste your time with the calculation, if you do that, you will find that it's 2/3. If I plug in negative 1 for x, I would end up with negative 9/4. And if I plug in 1 for x, I'm going to end up with 5 halves. So we're going to plot all these points on our graph to help us figure out where our curves are going to go. So we've got a point at negative 6, negative 1. We've also got a point at negative 9 halves and 2/3, which is a little hard for me to put in here, but that'd be right about there. We've got a point at negative 1 and negative 9/4. and we've got a point at 1 and 5 halves. So 1. So now we can actually put it all together to finish up our graph. Because we know that we have to always be approaching the asymptotes and go through any existing points. So for example, on the far left side, we're going to start at that point and trend along both asymptotes. And same thing on the far right side here. And obviously we want to never cross or touch the asymptotes. Hopefully your graphs will be a little bit better than mine. Now in the middle, we can cross the asymptote, but we have to follow the vertical asymptotes. So for example, I can see that we're going to go through a point here, which means we trend upwards. On the other side, we have to go through that blue point, which means we trend downwards. And that gives us the overall picture for our general rational function. And you can see this is a little bit more complicated than the function that we looked at back in 9.2. So let's look at one more example together. Imagine that we had the function h of x equals 3x squared minus 48 over x squared plus 4x minus 32. So we're going to go through each of the 9 steps again together. The first step is we want to factor if necessary and determine the domain. And we certainly want to do that. So in the numerator, we can factor out 3, and we'd be left with x squared minus 16, which factors even further into x minus 4 times x plus 4. This is part of why we spent so much time factoring in chapter 5. In the denominator, we can factor this quadratic into x plus 8 times x minus 4. And I can see here that some things cancel out. X minus 4 cancels with x minus 4, and we're left with 3 times x plus 4 over x plus 8. So it's actually a much simpler function in that case. Still a rational function, just simpler. So our domain here, when we think about the domain, it's really important that you don't look at the end after you've canceled things out, but instead you look at either the beginning or the middle factored version. Because in this case, x cannot equal 4, but x can also not equal negative 8, because negative 8 was going to cause a problem in the original rational function. So we do, however, have holes this time. So step 2 says find the holes and plot them. The holes exist wherever something canceled out in the numerator and denominator. So in this case, our hole is at x equals 4. And we want to know the y coordinate as well, so we need to check f of 4. And we can do that in the factored and canceled version. So f of 4 would be pretty simple to find, because it would just be 3 multiplied by x plus 4. So in other words, it would just be 3 times 16. Or sorry, I apologize. 3 times 8. So we've got 24 over 4 plus 8, which is 12. So in other words, our hole would exist at 4, 2 in this case. And then our vertical asymptote would be the other numerator spot that didn't occur in our domain. So in other words, our vertical asymptote is going to exist at x equals negative 8. So I'm going to plot those two things first. So we've got a vertical asymptote at negative 8. And we also know that we're going to have a hole that exists at the point 4, 2. 1, 2, 3, 4. And that's important because our function has to go through that hole, so that gives us a lot of information. So then in terms of our x and y intercepts, it's easiest here if you find those from the factored version. So in other words, we've got, for the x-intercept, remember that we just need to focus on the numerator. So we know that 0 equals 3 times x plus 4. So that tells us that x equals negative 4. So we've got a x intercept at negative 4 comma 0. So I'm going to plot that point on here as well. 1, 2, 3, 4, negative 4 comma 0. And then we have a y-intercept when we plug in 0 for x. And if you do that into the final factored version, you would see that you have 3 times 4, which is 12, over 8. So in other words, we would have a y-intercept at 12 over 8, or in other words, 3 halves. So we're going to plot that on here as well. So we've got our y-intercept right there. And then the last piece here is our horizontal asymptote. And you can see that the degree of the numerator matches the degree of the denominator. So in this case, because we have the same degree, we know that the horizontal asymptote is just going to be the ratio of our leading coefficients. So in other words, y equals 3 over 1, or in other words, just 3. So I'm going to put in a horizontal asymptote as well. So at this point, we can actually simply draw in our function. Because the interval, if you think about it, we've got enough information here to know that our curve on this side has to come through the points as well as the hole. And the curve on the other side has to be reflected by symmetry with that first curve. So in this case, our interval table is not needed because we don't actually have a situation where we need more information to plot points. So one takeaway from this is that we only need an interval table when we have 2 or more vertical asymptotes. That's the only time that we actually need that, that interval table as one of our steps. So you've seen a couple more examples here today, and you're going to practice a lot more examples on your homework tonight. Let me know if you have any questions.